Industry skills, practical knowledge, real-world impact. This is Simple Gyan.
Imagine this, a handful of ordinary sand, the same sand you walk on, can power an entire city. No fuel, no smoke, no noise, just the silent power of the sun captured in stone. But how? How does raw quartz transform into a high-efficiency solar panel that generates electricity for 25 plus years? Today, we go deep into that journey. At its core, a solar panel works on the photovoltaic effect. It's the science of turning light directly into movement. When sunlight hits a semiconductor like silicon, it knocks electrons loose, creating a flow of electric current. But not all silicon is equal. To achieve high efficiency, we need silicon that is ultra-pure and structurally perfect. That journey starts with quartz, or silicon dioxide, found in sand, rocks, and mountains across the globe. For solar cells, we don't use ordinary sand. We use high-purity quartz with minimal iron or aluminum impurities. Even tiny impurities can reduce solar panel efficiency significantly, trapping electrons before they can work. Step 1. Quartz is converted into silicon using a massive electric arc furnace at extreme temperatures. Inside, quartz and carbon in the form of coal are heated to approximately 2000 degrees Celsius. This chemical reaction produces metallurgical-grade silicon, which is about 98 to 99% pure. But 99% isn't enough for solar. We need electronic-grade purity, what we call 9-9's purity. Next is chemical purification via the Siemens process. Silicon reacts with acid to form trichlorosilane. This trichlorosilane gas is purified through multiple stages of distillation to remove every trace of impurity. The purified gas is then decomposed at high temperatures, depositing ultra-pure silicon onto heated rods. This produces polysilicon. At 9-9 purity, it is one of the cleanest substances ever manufactured by humans. Now, this polysilicon is melted down again to grow the structured crystals needed for electricity. The Czochralski process begins with a single seed crystal dipped into the molten pool of pure silicon. As the rod is slowly pulled upward and rotated, a perfect single crystal ingot begins to form. This monocrystalline structure allows electrons to move freely, resulting in much higher energy efficiency. These massive ingots are sliced into ultra-thin wafers using precision wire saws coated in diamond dust. Each wafer is just 150 microns thick, so thin that they are actually somewhat flexible and translucent. The wafers are cleaned and textured to create tiny pyramids on the surface that trap incoming sunlight. Now for the magic, doping. We add phosphorus to the surface to create an N-type layer with extra electrons. This creates the PN junction, a permanent internal electric field that forces electrons to flow in one direction. An anti-reflective coating is applied, giving the cells their iconic blue color while maximizing light absorption. Fine silver grids are printed onto the top and aluminum on the back to collect the electricity generated. This is now a working solar cell, capable of turning sunlight into a measurable electric current. Individual cells are connected in series using copper ribbons to increase the overall voltage and power. The cells are sandwiched between protective layers of tempered glass and durable polymer backsheets. In a vacuum laminator, these layers are fused together to protect the delicate cells from the elements for decades. An aluminum frame is added for structural strength, and a junction box is installed to output the power. Finally, every panel undergoes a flash test under standard conditions to verify its power output and efficiency. But the engineering doesn't stop there. Bifacial panels now capture light reflected from the ground, increasing output. New materials like perovskite are pushing efficiencies beyond 30% in laboratories around the world. Countries are rapidly scaling this infrastructure, moving toward a future of complete energy independence. And the biggest advantage? The fuel, the sunlight, is absolutely free and completely inexhaustible. From sand to silicon to sunlight-powered electricity. This is one of history's greatest engineering feats. If you love deep engineering content, subscribe to Simple Gyan. We break complexity down to the core.